Hi, I'm Junya Nose. I'm a master's student at Tokyo Institute of Technology. I'm building a beginner-friendly environment based on the program design recipe. Today, I'm going to give you an overview of my project and tell you about the feedback functionality of my environment. The program design recipe is a sequence of steps for systematically designing functions. The design recipe consists of 6 steps. Suppose we are given a simple problem like this. Compute the sum of a given integer list. We begin by defining integer list as a data type with 2 clauses, empty and cons. We then create examples of integer lists, such as empty, a singleton list containing 1, and 2-element list containing 1 and 2. Next, we write the purpose, signature, and header of some function. Here the purpose is to compute the sum of an integer list. The input type of sum is list of int, and the output type is int. The header of the function is a definition with a dummy value, which in this case is the integer 0. Before defining the function, we create several input-output examples using the data examples from step 1. We also develop a template. A template is an outline of the function definition, which describes how to process the input. Then, based on the template, we complete the function definition. And lastly, we run the test and see whether the function behaves as expected. If all tests are passed, that means we are done. The design recipe is helpful for beginners because it tells them what to do to solve a problem. In fact, the design recipe is used in many universities, such as Northeastern, Brown, Indiana, Tübingen, and our school, Tokyo Institute of Technology. However, the existing programming environments do not provide enough support for design recipe-based programming. Specifically, there are 2 problems. First, the student may skip early steps and directly start coding. It's not surprising, because for students, the most important thing is to have a program that works. Second, even if they follow the design recipe, they'll not always be able to check whether the outcome of each step is appropriate or not. It's partly because some of the intermediate outcomes, such as data definition and function template, are not written as runnable code. As a solution to these problems, we propose to build a programming environment specialized for running with the design recipe. The environment covers all steps of the design recipe, and in each of them, it gives the programmer guidance on what to do, as well as feedback on inputs from the programmer. For instance, when the user presses the button for creating an input-output example, the environment automatically inserts into the editor a function for creating examples, and asks the user to fill in the gray parts. And when the user requests feedback, the feedback generator checks whether the user's input is appropriate or not. In this case, the input-output example only covers the cons case, so the feedback generator complains that there is no example whose input is empty. After receiving the feedback, the user will create an example for the empty case. Now, the feedback generator says the examples are all exhaustive. In this talk, I will detail the behavior of the feedback generator. To build a feedback generator, as well as other components of our environment, we create a domain-specific language, DSL. We use the DSL as intermediate language between the user's input and the feedback generator. There are several advantages of this approach. For instance, by organizing the user's input as a data structure, we can systematically compute the feedback on the input instead of directly manipulating plain text. Moreover, by having DSL as an intermediate language, we can support various programming languages with less efforts, because we just need to define a translation from the user's input into the DSL. Now, let me show you how our feedback generator works. Suppose the student is assigned a task like this. Define the function SUMTree that calculates the sum of the values in a given binary tree with the integer values. I'm going to show you the feedback in step 1, step 3, and step 4, which are supported by the current DSL. We first look at the feedback on the data definition. Here is a correct data definition of binary trees. We have two clauses in this definition. The first clause, leaf, takes no argument. The second clause, node, takes 3 arguments, and among them, the first and third ones are recursive. In How to Design Programs, which is a textbook that introduces the design recipe, a data type definition is required to meet 2 requirements. First, the definition must have one or more clauses. First, the definition must consist of 2 or more clauses. Second, the definition must have one or more clauses that do not refer to the data type being defined. Now, suppose the student writes a data definition that only has a node clause. In this case, our DSL provides an error message. There is only one clause, and there must be one clause that does not refer to binary tree. We next look at the feedback on data examples. Here is a good set of examples of binary tree data type. The first example is just a leaf, and second one is a larger tree. In How to Design Programs, there is one explicit requirement for data examples. That is, the examples must cover all the clauses of the data type. In addition to this, there is an implicit requirement. The examples must contain a large example. Large means that has nested use of recursive constructor. We call the second requirement implicit, because the book does not actually state it, but we can see from the book that it encourages the student to create such examples. Now, suppose the student created 2 examples of node. In this case, Our DSL complains that there is no data example constructed with leaf. Next, suppose a student created one example for each clause, but without nested use of node. In this case, our DSL reports that there is no large example. Now we skip step 2, where we currently provide no feedback and move on to step 3. The third step of the design recipe is input-output examples. This is an example of correct input-output examples of the sum tree function. There are 3 examples. The first one is for the leaf clause, and the remaining ones for the node clause. The criteria for input-output examples are basically the same as that for data examples. They must cover all the clauses of the data type and must use large data examples as input. So, if the student only provides examples for node, our DSL says there is no example whose input is leaf. And if the student only provided a minimal example of node, our DSL says there is no example with a larger input. Now, let me show you the feedback on templates. This is the correct template of sum tree. The template has 2 clauses, because the binary tree data type has 2 clauses. In each clause, there is a list of things available for use in that specific clause. For the leaf clause, the list is empty, because leaf takes no argument. For the node clause, the list has 3 elements, which are the result of recursive calls on left and right, and the value argument in the middle. More generally, a function template must satisfy 3 requirements. First, it must start with a conditional expression covering all clauses of data type. Second, it must extract all constructor arguments. And thirdly, it must insert recursive calls on recursive arguments of the constructor. As an example of an incorrect template, this template only has the node clause. In such a case, our DSL complains there is no clause for leaf. As a different example, here is a template where the value argument is not extracted. In this case, our DSL warns there are missing constructor arguments. And lastly, this template lacks a recursive call on right, which is a recursive argument of the node constructor. In this case, our DSL warns there are missing recursive calls. Now, we are left with the coding and testing steps, but we don't go through them today, since we currently do not provide any feedback in these steps. So far, we have implemented a feedback generator that supports structurally recursive functions, and that provides simple feedback on data definition, data examples, input-output examples, and function templates. As a future work, we intend to support more advanced forms of recursion. These include nested data type, such as list of lists, mutual recursion like even and odd, and accumulative recursion used in the list reversing function. In how to design programs There are design recipes for these forms of recursion, and we would like to incorporate those into our DSL. We also plan to provide more support in each step, as well as to create an IDE. Let me share our ideas on these. In the first step, we would like to add a button for writing the interpretation of data examples, like this. The interpretation is in natural language, so it might be hard to evaluate it. But even if there is no feedback, we believe that writing interpretation would enhance the programmer's understanding of data types. A similar support could be integrated into the template step as well. More precisely, we add a button for writing the interpretation of recursive calls. It would help the programmer figure out how to combine those results to produce an answer. In the coding step, we would like to borrow Feldman's work to allow the programmer to ask, "Am I on the right track?" The idea is to synthesize the function definition using the input-output examples defined in step 3 and an incomplete definition developed in step 5. If the synthesis succeeds, the feedback generator says the user is on the right track. Of course, it is not always possible to finish synthesis before timeout. But since our environment forces the user to write a template before coding, we might be able to shorten the amount of time required for synthesis. For the IDE, there are different design choices. The first choice to make is to what extent we force the programmer to follow the design recipe. Suppose the programmer has written a correct data definition. At this point, we could either enable all the buttons for future steps or enable only the one for data examples. We prefer the latter because we believe that the fastest way to learn how to design programs is to always follow all the steps of the design recipe. Another choice to make is whether or not to automatically show the feedback. For instance, when creating data examples, the programmer might wish to see whether the examples are exhaustive without pressing the feedback button. On the other hand, the programmer might also wish not to see a negative feedback when they know they are not ready. To summarize, I have presented a feedback generator for design recipe-based programming. There are still lots of things left to be done, and I welcome any ideas and suggestions on the design of our programming environment. Thank you.
Thank you, Junya.
Thank you.
Very interesting talk, and there are several questions in the Q&A section. I will read them out to you in the order of the upvotes. So I'll start with a question.
Can you hear me?
Yes, I can hear you. Okay, so I'll start with the question of Teine Zhao. Do the tests actually get
Is the network working?
Yes, I hear you. Can you hear me? Can you hear me?
Oh, okay, thank you. But I can't hear your voice.
Okay. So I'm not quite sure how to get in touch with you if you can't hear me.
Oh, okay. I can reload. I try reload.
Can you hear me now? Okay, I guess Junyan will join back in a few seconds. Sorry for the technical problems. Junya, can you hear me?
Yeah, okay. I can hear your voice.
Okay, fine.
Okay.
So there are quite a few questions, and I don't think we'll take them all, but I'll take the most upvoted ones. The first one is, do the tests actually get executed? And if so, are there any concerns with termination?
Sorry, one more, please.
So do the tests actually get executed? And if so, do you worry about termination? Termination of the tests?
Oh, in the coding step, am I on the right track steps?
So the question is, do the tests get executed?
Oh, yeah. I think it's not. Sorry, I think it never stop because I support structural recursion. So so it always stop. Okay, I answer. It is not. It is never stop. If the user if the user has written a complete template, the program must terminate.
Okay, are you saying there's a time limit? I'm sorry, I didn't quite understand.
Okay, sorry. I talk about structurally recursive function. We only support structural recursion. So if the user's template is correct, the program must terminate.
Okay, I'm sorry, but I think the 25 minutes is pretty much over, and there are many questions, but I think maybe it's best if you handle them offline. So I want to thank you for your presentation, and we'll move on to the next presentation. So thank you very much, Junya.